aimed towards the second exam. And so we are completely changing gears. We're almost completely abandoning vectors for a while because that's not our emphasis. So probably the next 2 months now, we're looking at three-dimensional things and not movement so much as surfaces and things of this nature. So we're now embarking on functions, really right now, of 2 variables. We can have functions of 3 variables, and we will look at those also, but our primary concern is functions of 2 variables. What that means is you have 2 independent variables as your input, and you still have 1 variable as your output. But this automatically makes it 3-dimensional because you now have 3 variables. Remember, dimension is, don't think of dimension as a geometric thing. Dimension is always just simply how many variables are involved in the problem. So if I gave you 3 independent variables, then you have a function of 3 variables. That makes it a 4-dimensional problem. That doesn't make the math more complicated. It just means I can't draw you a picture of the result. You know, that's not a big deal. So we're going to primarily concern with this. So right off the bat, we write things like this. We say z is a function of x and y, and this is how we write it. This means that x and y are both independent variables. X is not a function of y is not a function of x. Technically, they could both be functions of a parameter, like t, and we will look at things of that nature as we go, but for right now, purely independent variables. So in Calc 1, one of the things I emphasize from day 1 of Calc 1, every time you do a Calc 1 problem, whether it's just simply take a derivative or you're doing an application problem, I always tell the students, before you even start the problem, identify the domain. And all of you have probably experienced this. You're doing some form of application, maybe finding the extrema or something, and you give an answer, and it turns out that answer is impossible because that's not in the domain. Right? We're doing an application problem, you know, how many widgets should we produce to maximize the profits? And you come up with an answer that's a great answer, but it's actually not possible mathematically to do that because it's outside the domain. You always start by asking the question, what is the domain, so I know what my set of values can be? Our favorite domain in calculus is always what? It's our favorite domain.
Negative infinity and positive.
Yeah, all real numbers. Our favorite domain is all real numbers because that simply means there are no restrictions. Is that always the case that it's all real numbers? No, not if I have stuff involved. You know, if there's anything interesting, if I have a quotient, right? If I have a root, if I, you know. So let's start with a simple Calc 1 question. In Calc 1, let's start again. Really, something really, really simple. Let's say this is the function I'm working with. I'm going to take derivatives, I'm going to set them equal to 0, I'm going to find inflection points, I'm going to do all sorts of stuff. But before I start, I'd like to know what can I actually use? Because otherwise, it's possible that I could give an answer that's impossible. I did great algebra after the fact, but I ignored the fact that I have restrictions here. So if I asked for the domain of this, how would you start the problem? You know, you're going to do some algebra off to the side. Probably going to attack the argument. Tell me about the quantity x squared minus 9. Does it have any restrictions?
It has to be greater than 0, or it can't be negative.
So be more specific. You were right. So is there an inequality maybe? What do you think?
It has to be greater or equal to 0.
Beautiful. Greater than or equals 0 is okay. If that quantity was in a denominator, no, then I couldn't do the 0. Now, if we're in an upper level class, a higher level class, would we put a restriction on this in actuality? No, because complex numbers are totally okay in the big picture. But we are doing what is called real valued calculus. That is not a joke when I say that. Real valued calculus simply means all inputs and all outputs have to be real numbers. There actually is no such thing as a restriction that makes things have to be real numbers. That actually isn't true in general, but we need to learn the calculus of real numbers before we can expand to the calculus of complex numbers. And who here would ever take a class like that? How many are engineering bound? All of you, that's your first upper division class. It's called complex analysis. It's the calculus of complex numbers. And it's all of calculus now applied to complex numbers. And there's no such thing as a restriction on any question that exists. And that's the problem you're going to do for the rest of your life in engineering. Because there's no such thing as a restriction. Oh my goodness. But if I don't understand the real numbers, I definitely can't extend it to complex. If I don't understand 2 dimensions, I can't extend it to 3. So we have to learn certain things in order. Real value calculus says I can only have real outputs. That's why we put this restriction on here. If I was allowed to have complex numbers, I can have complex input and complex output, which now means the entire set of complex numbers is my domain. The entire set of complex numbers. Anything's fair game. So, let's keep going. X squared's got to be greater than or equal to 9, so the absolute value of x has got to be greater than or equal to 3. Now, go back to baby algebra. Don't try to think about this in your head too much. In baby algebra, what do? Draw a number line. Let's see. Anything else?
-3.
That way? No. As the negative numbers get big, the absolute value of the negative number is greater than or equal to 3, isn't it? Oh, so basically we've created a gap here. In words, you'd say all real numbers except the ones between -3 and 3. Do you agree? So generally speaking, whenever you wrote a domain, you always wrote it as intervals. You don't write a domain as an inequality because, first of all, a domain does not involve a variable. A domain is simply, what of the set of real numbers, which ones do I get to use? There's never a variable in that statement. When in baby algebra, they'll often say, "Oh, use a variable." Well, why would it matter? Because whatever letter of the alphabet I use here doesn't change the domain, does it? The domain is still coming from this picture. So rather than worry about the letter of the alphabet, just simply say the domain is everything from -infinity to -3, and from 3 to infinity, open or closed? Closed. And I put union, because I'm putting the two together. Intersection would be an empty set because there's no overlap. So that's what we did in baby algebra, right? That's what we did in Calc 1. That's not what we're going to do now, because now my inputs are x's and y's. So right now, in everything you've ever done as a domain was always what values on the number line can you use. But now my domain's going to be what ordered pairs can I use. Ooh. So that changes from the number line to what? The entire xy plane. Now my domain comes from the xy plane. That's different, isn't it? So it means how I answer the question is completely different. So let's suppose I said that z, which equals f of x comma y, is equal to, how about the natural log of x plus y? Okay? Now, I don't care what this looks like. I just want to know what can I use as input. Now, you could say, well, x can't be negative. Are you sure? Are you sure x can't be negative? Can x be negative? As long as y makes up for it. What can't be negative? X plus y. Can x plus y be 0? So what restriction will this have? And think of this as the algebra off to the side part like we did over there. What would you say? X plus y has to be strictly greater than 0. Now, does that present an infinite number of options here? Yeah, one of the things I like to do in this problem, I like to draw a picture. See, I drew a picture here that made it easier for me to interpret. This isn't the answer, this is. But this picture helped me. Can you draw a picture where x plus y is greater than 0? Yeah. Like in baby algebra, I'd be shading half of the xy plane, wouldn't I? Now, can I give this answer as an interval? No, because technically can't x be any real number? And y could be any real number, but it's not the whole xy plane. So answering this question is a little bit different because I can't answer it using intervals. I have to answer it using ordered pairs. So it's actually pretty simple. I go back to this. So we'd say the domain now, we're using something called set builder notation, which you probably haven't used since you maybe, pre-algebra. You don't use set builder notation for anything generally in an algebra class. But in a calculus situation, we're saying the set of all ordered pairs such that. Vertical bar means such that x plus y is greater than 0. That's all I gotta say. Could you say such that x is greater than negative y? Could you say that? Could you say such that y is greater than negative x? Could you say that also? Yeah. Are you saying the exact same thing all 3 times? Yeah, so it doesn't matter. But that's it. I'm saying the set of all ordered pairs such that. Now the set notation means I'm saying it's a set. If I were to answer it in this case here, if I use set builder notation, which is what they actually use in the algebra books, but I don't like set builder notation in the algebra books because if you use set builder notation, you will never learn how to do an interval. Set builder notation means you don't use intervals, ever. But an interval answer is what we call the right answer. We don't need to write it lengthy. But in set builder notation, this would be saying the set of all, now I can say x's, the set of all, this doesn't mean the set of all x's, this is the set of all real numbers. It wouldn't matter what letter of the alphabet I put it there. By putting one symbol there, it automatically means a set of real numbers. Well, what does this mean over here? This is the set of all, what did I say? Ordered pairs, which means real number, comma, real number. Oh, so in English, this is the set of all ordered pairs. This is the set of all individual values. The default is automatically that x is from the set of real numbers, by the way. There are other classes where the default might be it's from the set of complex numbers, or it's from the set of rational numbers. In a discrete math class, we often make the default rational numbers as opposed to real numbers because of the nature, such that the absolute value of x is greater than or equal to 3. The set of all real numbers such that the absolute value of that number is greater than or equal to 3. Is that the same thing that I have here? Absolutely. But if you were in an algebra class, is this entirely helpful? Do you know exactly what real numbers you get to use? No, you still would have to figure it out, wouldn't you? Is it possible that I could use the wrong values? Yeah. So I don't like this. Every algebra book will tell you this is the domain, but then you don't learn how to do an interval. You need intervals. But here I can't give you intervals because clearly x can be any real number as long as it's still bigger than the negative value of y. And y can be any real number as long as it's bigger than the negative value of x. So saying, well, x and y can be anything isn't useful. Okay, that's not useful. So I'm saying, no, the set of all ordered pairs such that this is true. You never have to draw the picture. But sometimes drawing a picture can make it easier to interpret. Sometimes it just, because you might have multiple things going on. Let me do one more example. This is not complicated in any way, talking about domains. But I just want to teach you how to do it correctly. So I might say, all right, z is, let's say now we have, how about 1 over the square, actually no, let's say, not 1 over, how about the square root of x over the square root of x times y plus x. No, plus y. What am I doing? Not plus x. All right. Oh, that's just horrible looking, isn't it? That's terrible. Why is this terrible? Well, that's really not, I mean, the numerator is real easy, the denominator is real easy, but they both have to be true simultaneously. Oh, that means I'm going to have an intersection of things. And that automatically makes it a little more challenging. So I want to show you how to do that. So let's treat this as 2 completely separate problems. For my numerator, do I have any restrictions on my numerator?
Greater than 0.
X has to be greater than 0. Do I have any restrictions on the denominator?
X plus y is greater than 0.
How about xy plus y?
Has to be greater than 0.
That's to be greater than 0. Now, are you happy with both of these statements so far? You should not be entirely happy with both of them. One of them is not exactly correct.
The first one should be greater than or equal.
Or equal, yeah. We sometimes forget it. You can have a square root of 0. You just can't be in the denominator. Now, does that change things? I don't know. Maybe it does. Now, I just wrote 2 statements up there. Is there something that should go in between them? Sometimes we forget this one. How many have written any code? Any kind of computer? Okay, there are probably, some people say, arguably the three most important words when you're writing computer codes. And, or, and probably the most important word, not. Does that change things? A and B, A or B, not A, not B. Yeah, it's astronomically huge. And or are astronomically huge in terms of their difference. And means intersection, overlap, it's extremely exclusive. Or means union, combined, it's extremely inclusive. If any part of an or is true, then the entire or is true. If any part of an and is not true, the entire and is not true. And a lot of times we treat them as the same thing. There is no context where they are the same thing. They're very different. So the example I always give is, all right, I went for a job interview last week. And like any good job interview, I'm actually interviewing the people, you know, at that long table with the, you know, the mean faces. I'm interviewing them to see if they're worthy of having me as an employee. So before they start, I said, I have a few demands. All right, I want 7-figure salary. I want keys to the executive washroom. I want my own parking place. And I want the letter M stricken from all company language. And so then they discuss it among themselves. And they said, well, it's kind of limited around here. We can do everything except the parking space. Am I going to take the job? Why?
You said and?
Because I used the word and, which means all of them have to be true at the same time for the entire thing to be true. And is exclusive. If you thought about it in circles, like a Venn diagram, it's all the overlapping circles, it's the innermost part. Now, I come back the following week for the interview with my tail between my legs and say, okay, I've changed my demands. Okay, 7-figure salary, or keys to the executive washroom, or the parking place, or the letter M thing. And they get together and they say, we can do keys to the executive washroom. Will I take the job? Yes. Why? Because I said or, which means if any part of it was true, it's all true. Never confuse the roles of and or. Anybody who's written computer code understands this. And versus or, it's a world of difference. And not is even more important because the word not now means you're looking at the complement, which is not something we spend a lot of time in this class on, but we do spend that time in many other classes. So there's a word that I want to see here, and it matters. And. Because both of these have to be true simultaneously. Now, whether you remember this or not, in baby algebra, do you remember graphing inequalities, linear inequalities? And you might have had 2 or 3, and you're graphing them, and hopefully you didn't write too dark, because all of a sudden you've just filled up the entire graph paper, or you shaded everything. But the answer was probably the overlap. But the answer, it might have been a union question, it might have been an or, in which case you probably are shading everything. It did matter, didn't it? So if I had combined inequalities, baby algebra, I have, y is greater than 3, and I have x minus y is less than 2. So I have 2 inequalities going on at the same time. Now, remember in baby algebra, you're like, okay, this is kind of hard to read. Now, what is my final answer?
You don't know.
You don't know. Why not?
It doesn't specify if it's and
Oh, okay.
or.
If it had been and, then my answer would be what? Basically, this, do you agree? That's the overlapping region. But if my word had been or, then the answer is all of this. Does that make a difference? Yeah, it's astronomical. And mathematically, it's huge. Putting an or here is a completely different result, and it's probably not going to be the case most of the time. It's probably going to be an and most of the time. But if you don't write anything, the default is an or. Baby algebra, let me keep it real simple. X squared equals 9. So x equals 3 comma negative 3. That's how most of us would write an answer. Agreed? Can x be 3 and negative 3 at the same time? No, that would be impossible. Comma always, in every context, means or. I have two answers, x is 3 or x is negative 3. And when I'm doing algebra, I will actually write x equals 3 or x equals negative 3 and then show them you can shortcut by just putting a comma. But writing the word or is absolutely correct. But mathematically speaking, in a calculus class, the comma still means or. So if you want and, don't use a comma. Okay? Because you're actually saying or. This is always interpreted as an or. Okay? Why? Because x cannot take on two values at the same time, but it could be one or the other. Why is this, or this? Because there is no real number that is simultaneously less than negative 3 and greater than positive 3 at the same time. Ah. So, by the way, I don't have enough here. There's got to be more. X is greater than or equal to 0 and xy plus y is greater than 0. If I don't know anything else, can I state both of these? Yeah. Now, is it possible that I could put those together and figure out something else? For example, is it possible maybe I can do this? Huh. So tell me, I already have this one down. Give me more information here. Algebra, not calculus. For this product to be positive, tell me about the quantities. For the product to be positive,
X plus 1 has to be greater than 0?
does it?
X has to be greater than 0.
For the product to be positive, I have a product of two things. For the product to be positive, tell me about my two things. They have to be
Positive.
the same sign. They could both be negative. That's okay. Oh, but we said x has to be greater than or equal to 0. So if we're saying x, remember we said x had to be greater than or equal to 0. Just look at this for a moment. This says x and y. By the way, y cannot be 0. Do we agree? Could x be 0?
Yes.
Yeah, x could be 0. That's not a thing. Each of these quantities have to be the same sign. But because x had to be greater than or equal to 0, x plus 1 is always positive, isn't it? Oh, so does that mean now y has to always be positive? I think we just figured out our domain, folks. The domain is this. We had to do a little bit of algebra, be a little bit clever. Now, what does that look like graphically?
First quadrant.
It's more or less it's the first quadrant including the y-axis. But it's pretty much the first quadrant. It's not nebulous whole xy plane. This is why sometimes messing around doing a little bit of algebra can help you. Okay, now I have a better interpretation. Clearly, neither one of these variables is ever going to be negative in this picture. Okay? So, figuring out domain is simply how do I express it? That's it. There's no calculus involved here. So, let's move on from that. Now, we have a function of two variables. I'm going to go out on a limb here and say, if you knew how to work with functions of two variables, then a lot of the Calc 1 you did, particularly the stuff that gave you the most trouble, probably wouldn't be nearly as difficult. In Calc 1, and technically Calc 2, but mostly Calc 1, what types of things did we least like working with? I'll give you a hint in case you can't remember. Did you like working with circles in Calc 1? No. Why? Circles are great to work with, generally. Great in geometry, terrible in calculus. Why is a circle terrible in Calc 1?
Because you would take a derivative or an integral and keep coming back.
Well, even back up. Why is taking a derivative of a circle extremely difficult in general?
Because it's not a function.
It's not a function. Yeah, we love circles. We hate them in calculus because they're not functions. So go back to Calc 1. You hated working with anything that was not a function because taking derivatives meant implicit differentiation. Sometimes it meant I had to do all sorts of other things. We didn't like working with non-functions. Let's put it that way. Am I right on that one? You hated working with non-functions because all of your rules, all your derivative rules were always derivatives of functions. Y equals f of x, here's what the derivative is. But if it was not a function, then I cannot isolate the y, then I can't take the derivative that way. What if I told you that every single thing that exists that you could possibly put in 2 dimensions is a function? including circles. Heck, even figure eights, although we're not going to work with figure eights. Anything you could draw in 2 dimensions is a function. I know that's not true. Well, I didn't say a function in 2 dimensions. A function in 3. And now I'm going to go a step further. Everything you ever did in 2 dimensions is something in 3 dimensions. But you're looking at something called a level curve. I'm going to define this. Okay? I'm going to make this really clear what a level curve is, and then I'm going to show you that everything you've ever done in 2 dimensions actually is what's called a level curve of something in 3. You didn't know it came from 3, but I'm going to show you how you can work backwards. All right, the simplest example that I can give you. All right. This is a map. You know, I might be looking at, like Borrego Springs. I have this really huge flat plain, but then I have little mountains. And let's say that this ring represents, 1,000 feet of elevation, and this one's 2,000 feet, and this one's 3,000 feet. So this is 1, 2, and 3. This is 1, 2, 3, and this top one is 4,000. Anybody ever seen a map that looked like this? Yeah, what's this called?
Contour map.
That's another word. Topographical. It actually comes from a mathematical term, topography. It's a topographical map. It's contour map. Those are called contour lines, which is really funny because they're not lines at all. If I looked at this, is it pretty easy to say, oh, this is a mountain that's coming out 4,000 feet. It's kind of obvious. But I've drawn a 2-dimensional picture. And everybody has no problem with this. But think now, I'm taking the entire landscape and I'm taking slices. So I took a slice 1,000 feet off the ground, and this is what the rim of that slice looked like. And then the same thing at 2,000 and 3,000. When I'm looking at that map, can you in your mind put together what it looks like, in a sense? Yeah, the topography of the land. That's not that hard to do. Each of these are called a level curve. Each of these are a slice of the mountain, and I'm looking at the rim of the slice. That's it. That's not a calculus question. That's what it is. I took a 3-dimensional thing, but I wrote it in 2D. Well, actually, let me do this. Sorry. Let me do it this one. Keep it simple. Okay. My personal favorite. Okay. This is my favorite graph to work with because I can draw it fairly easily. Okay. What this looks like it's a circular paraboloid. We know that. Okay? How do we know that? Because when I look at that, I can see the cross sections. In the XZ plane, they're parabolas, in the YZ plane, they're parabolas, and in the XY plane, they're circles. This is why I said last week that you have to be able to look at a function and know what it is instantaneously. And people say, well, I'll just memorize. Really? That's like memorizing the answer to every conceivable question that could be asked. But the problem is that's infinity squared, and that's probably not a good use of your memory storage. No, look at it, figure it out in 2 seconds, and then move on. How do I figure it out in 2 seconds? Parabola, parabola, circle. That's really not that hard. Right, the other variable is held constant. The other variable is never 0. Ever. And some people actually are giving me answers still saying, no, I learned this. I watched a YouTube video. I wouldn't watch that video. No, the variable cannot be 0 because you can't get a cross section. If any of these variables are 0, for example, if z is 0, then I'm at the origin at 1 point. I can't determine anything about anything from the origin as my only answer. No, but what if I said, I want you to consider z equals, just give me a number. Z is 9. Okay. Oh, I left my orange pens at home. Shoot. All right, I have no orange pens, so I'll do the black. Z equal 9 is a plane. Agreed? Don't ever make the mistake of taking a variable and thinking it's a value in 3 dimensions. No, this would be a plane in 3 dimensions. Z equals 9 means I'm 9 units off the ground forever. So I'm slicing this plane, and when I do that, do you all see a circle there? My slice. Think of this as a Jell-O mold, and I sliced it. You see a circle. You're standing on top of the z-axis. You are looking down. Somebody sliced it 9 units off the ground. Exactly what do you see? You see x squared plus y squared equals 9, which is a circle of radius 3. It's a 2-dimensional drawing. This is not 3-dimensional. This is 2-dimensional. X squared plus y squared equals 9 is simply a 2-dimensional circle. When I'm standing on top of the z-axis looking down, that's what I see. But this is not a function. But this is. This is a slice of this. Every circle that you could conceptualize is a slice of a circular paraboloid. All of them. Every ellipse you can conceptualize is a slice of an elliptical paraboloid, by the way. Every hyperbola you could imagine is going to be a slice of a hyperbolic paraboloid. Everything you can imagine in 2 dimensions is a slice of something in 3. But if the thing in 3 is a function, then maybe I can figure out a way to make things like derivatives easier. Yeah, we're going to do that. Implicit differentiation, you're going to laugh at. See, everybody here, if I said, what's your most hated form of differentiation? Duh, it's implicit differentiation. Everybody struggles with that. Because it's hard. It's so much more complicated. What if I told you implicit will be as easy as anything you've ever done from a derivative standpoint in a few days? You know, you're going to invite it to your next party. It's going to be your friend. Right? You're gonna FaceTime with implicit differentiation. I don't know if that's the right term. But anyway, you're gonna Instagram. You're gonna love implicit because you're gonna make it so easy and you're never gonna miss another problem because you're gonna look at it from a completely different point of view. You're gonna look at everything you ever did in 2 dimensions from a 3-dimensional point of view. And when you do that, it's gonna make things easier, not harder. Because we've been dealing with slices. You see, everything you've ever done in math is correct, but it was a little bit artificial. So what do you mean? In other words, you've been doing it like you're the cartoon character on the TV screen. They live in a 2-dimensional world, but you're looking at it in a 3-dimensional world. If you're in 2 dimensions, you can't conceptualize 3, but if you're in 3, you can easily conceptualize 2. But everything you do is actually 3-dimensional, isn't it? How many have had physics, at least? Yeah, of course, everything in physics is 2-dimensional, right? No, you don't do anything in 2 dimensions. And that's why things are harder at first, because you're not used to doing 3-dimensional math. So what we have to do is start thinking this way. So what a level curve is give me any function of 2 variables. I need it actually to be a function of 2 variables. And then simply pick a value. So for example, let me go back to this one. I want to find the level curve that passes through the point, how about 2, 3. That means my input is 2, 3. So what you have a circular parabola. It's coming out like this. It's, giant bloomin' onion, if you will. I have this circular paraboloid, okay? So it's coming out like this in all directions, this being the first octant, okay? I'm going to go on the floor 2 units, 3 units on the floor. Now when I input it, what z value will it go up to?
13.
13. Do we all agree that f of 2, 3 is simply 13? So if I said, what is the level curve that passes through 2, 3? You'd say it's x squared plus y squared equals 13. That is the only circle that contains the point 2, 3. How do I know that? Because any other input, right? 2, 3 can only give me one output because this is a function. So 2, 3 can only be on one circle. So I'm going to go up, remember this is the square of the radius, but I'm still going to go up 13 units up in the air, and I'll have a circle of radius root 13. Don't worry about that, but I get this circle if I use this input. So this is the level curve for this input because we started with this. So everything two-dimensional can be a level curve of something. And I'm going to show you how to do that. This is awesome. And we use this one all the time. I have something in 2 dimensions. And I'll start with a function, but it doesn't have to be a function. I have something in 2 dimensions. Let's say I have y equals f of x. Let's think of it if I put anything you want in there. Make f of x complicated, make f of x simple. Is this true? I've just made it 3-dimensional. When z is 0, that's one of my level curves. But now z can be anything. I've just created a three-dimensional function where this is a level curve, specifically the one when you choose z to be 0. Well, what if you chose z to be some other number? Now, first of all, you're looking at this going, this seems kind of sketchy. Okay, let me do a simple one. I don't want it to be too complicated. Let's say I have y equals, I don't know, let's keep it simple. Y equals x squared. Okay? So let z equal x squared minus y.
Could you also do y minus x squared?
It doesn't matter. You could do y minus x squared. I mean, excuse me. Because I want to subtract it and let z be the difference. Then z equals 0 is this. But now I have a 3-dimensional graph. Now I'm not good at drawing 3D. I'll make my best attempt here. Oops, sorry. Let me move this over a little bit. Let me move it over to here. If I was going to draw this in 3D, on the YZ plane, what do you see? So when z is a constant, then what do you see? You see y equals x squared with a plus or minus a constant. On the xy plane, that means you'd see parabolas, wouldn't you? So let me, I'd see parabolas forever and ever on this one, right? So what does that look like? Well, on the xz plane, I see parabolas. On the yz plane, I see lines. So I've got some goofy parabolic, I'm not even going to try to draw it. By the way, if anybody here has a graphing calculator, or you can go to computer, you can go to like GeoGebra, or even Desmos will do this really simply. And you can get a really good picture. And the reason I like those, like you can rotate it. So you're looking at something, going, I'm not sure what that looks like, and you can actually rotate the image. Has anyone ever seen those? Oh, it's too bad if you haven't done it. It's so easy. You just enter it and you say, let me rotate it and see what it looks like. But I've got some weird, goofy 3-dimensional thing. But you give me any real number for z, I now have a level curve, including z equals 0, by the way. What if you pick z equals 10? Well, if you pick z equals 10, isn't this going to be y equals x squared minus 10? Which is still a parabola. So any real number you choose for z, and by the way, I would choose the numbers for z, not for x and y in this case, because I started with the 2-dimensional thing. Oh, so that means that every real number for z is going to give me a parabola. Okay, z equals 0 gives me back the original parabola, but z equals anything else gives me back a parabola also. So all parabolas, therefore, can be considered level curves of something 3-dimensional. Now you say, well, that's so much extra work. But if I'm trying to do things in 3D in general, and we're going to talk about derivatives in 3D really soon, like next 2 classes are all about derivatives in 3D. Okay, so the idea of a level curve. Now, I mentioned before, you could have a function of 3 variables. This one's a little trickier because I can't draw a picture of this one. Suppose that, I'll call it W because we run out of letters. is f of x, y, z. And let's say, for example, that I want to do this. Now my domain would be ordered triples. My domain is not coming from the floor anymore, it's coming from entire XYZ space. Yikes. Would I have any restriction, do you think, on my domain, on my possible inputs? Since I'm squaring everything, would there be any restriction on my inputs? What do you think? Yes, no, maybe? No, I don't have roots, I don't have quotients, I don't have logs. I can put in anything. Now tell me about my output though.
Like 0.
Could be 0, but it can't be,
Less than 0.
yeah, it can't be negative, can it? So give me any positive number for W. Just make up a positive number for W. Okay, what about, W equals 16. Now what have I got? I have x squared plus y squared plus z squared is 16. Isn't that a sphere of radius 4 centered at the origin? Oh, so if you give me any particular value of W, what am I going to get? I'm going to get a sphere. But that's not a slice. That's not a... So what do I call this? This is called a level surface. It's not a level curve because it's three-dimensional. Now this is kind of crazy. That means everything in 3D is a level surface of something in 4D. Now I'm going to tell you something that's going to maybe hurt your brains, but it's necessary for you to understand this because this is how most of the important things have been derived. Okay, I have a point. It's between my fingers. I have a point. This is a line. The sun is up there. I'm going to line up the sun, line this perfectly with the sun, so the shadow you see on the floor is a point. Everybody understand what I'm doing? I have a line, and you see the shadow of this line is a point, clearly. Now, let me take a plane. I'm going to line it up perfectly with the sun, and it's going to make a shadow on the ground, which is a line. Now I'm going to take one of you. I'm going to have you stand there in the sun, and you're going to get really, really huge. And what does your shadow look like? Something two-dimensional. In other words, your shadow is, think of you being huge. Maybe you're a gigantic block, but your shadow looks like a plane, doesn't it? Cool. So what does that mean in simple English? You are the shadow of something four-dimensional. That's absolute. Every one of you here is the shadow of something four-dimensional. A point is the shadow of a line is the shadow of a plane is the shadow of anything three-dimensional, and anything three-dimensional must be a shadow of something four-dimensional. You can't think that way. The cartoon character on the TV screen can't think in 3D. It's one dimension too high. You can't think and conceptualize and picture things in 4D, but it's still there. So mathematically speaking, you are the shadow or a projection of something four-dimensional. Whoa. I know you're going to walk around all day saying, what does my four-dimensional me look like, right? But anything three-dimensional is simply a level surface of something four-dimensional. Do I have to know what this one looks like? No. But I have to know what the level surfaces are. Oh, okay. That's not that hard. And I can keep going in that way. Okay. I think I told you, some of you guys this. I read a book a few summers ago. It was called Y-E equals MC squared, and it was written by two Cambridge physicists, and the entire book is based on non-Euclidean four-dimensional vector calculus. And it was just kind of interesting because they said you don't need any math background or physics to understand. Yeah, you do. But in other words, all of Einstein's theories start basically four-dimensional. Yikes. I mean, how does he do stuff? And he's talking four-dimensional geometry, not just four-dimensional mathematics. So it's actually quite difficult to conceptualize a lot of these things, but that was what was necessary to come up with some of these notions. It's crazy stuff. So explaining what a level curve or a level surface is actually trivial. You're going to be given an equation, asked to input something, and now you have one less variable as a result. So if I had asked you to input an x, y, and a z, you would now have a constant for w, wouldn't you? So now you have x squared plus y squared plus z squared equals that constant, and that is now a very, very specific three-dimensional object. That's what the level surface is. The level curve is a very specific two-dimensional thing that came from the three dimensions. It was a slice. Okay? Everybody cool with that? So that's, you know, our brains aren't always ready for that sort of thinking, but this is where we're going. So now, we're going to start derivatives next day. But before we can do derivatives, think Calc 1. What did you have to sort of master before you discussed a derivative? Think topic-wise. Because you didn't start derivatives until maybe the third or fourth week.
Limits?
Limits. Yeah, and limits are always the key in calculus. We derive everything starting with the limits. And most of us here are probably pretty good when it comes to a limit. If you were working with a Calc 1 student and they had questions on, I don't know how to do this, you could probably walk them through. So let's do a Calc 1 problem. So let's suppose the question is something like this. We'll keep it really simple. The limit as x goes to 2 of, x squared minus 3x plus 2 over x squared minus 4. Now, a limit, and we always have to remind ourselves, a limit is not a functional value. A limit is where you're headed. And so it's saying, if I could get there. Now, a lot of times we have removable discontinuities. Sometimes we end up with asymptotic things. Sometimes we get weird stuff. Our favorite problems are things usually of this nature because the algebra isn't very hard. Now, if I just gave you a function and I said, what's the limit as x approaches a value, and you could evaluate the function at that number, you would. Because the functional value and the limit would be the same thing because nothing weird's happening. But I have a quotient, which automatically means because my denominator can equal 0, I have perhaps multiple discontinuities. For example, the domain of this is all real numbers except 2 or negative 2. Do you agree? And I've asked you to, okay, so this is not trivial. So there's two things I have to look at. If my denominator is 0 and my numerator is not, that's an asymptotic discontinuity. That's our least favorite. That means I have a vertical asymptote, and maybe I'm doing something like this. We hated those. Those were always kind of tricky. Or both numerator and denominator are tending to 0, in which case it's an indeterminate form 0 over 0, which was our favorite because that means probably a factor and cancel. It's a removable discontinuity. So what you always did first, the sort of the universal notation, we say it approaches what form. The form it approaches tells me my strategy. Remember, if it's not 0 over 0, that's one kind of conclusion. If it's 0 over 0, it's a different. Did we have infinity over infinity sometimes? Oh, yeah. In fact, if you now remember from Calc 2, there's exactly 6 different indeterminate forms. An indeterminate form means it's not only not a number, but you cannot evaluate it as is. You have to use other tools. The indeterminate forms we did in Calc 1 were the 0 over 0 and infinity over infinity forms. But then in Calc 2, we took things like this, then we manipulated the quotient, threw one of them in the denominators that's reciprocal. We had this one, which was always kind of weird. Two things which, and then of course the coolest ones, the ones that require L'Hopital's rule. This one and this one. Those are the exponential ones. Those you never had to use L'Hopital's rule in any limit you ever took, except for these. In fact, you never use L'Hopital's rule on this one. It'd be insane, right? I have a 37th degree polynomial over a 36th degree polynomial, which means I have to use L'Hopital's rule 36 times. Or I just look at degrees and give you the answer in 3 seconds. Yeah, you don't use L'Hopital's rule for 99.9% of them because it isn't faster, it takes you longer. And you can't use it on this one, you can only use it on these two, by the way. But then you manipulated these using exponential version of e to the log, you did all that stuff and got one of these to look like one of these and you use L'Hopital's rule. Because if you have a logarithm, there's no algebraic way you can do a limit. That one has to, that's the only one that you have to use L'Hopital's. So we love L'Hopital's because it was a great shortcut. If I put a 2 in the numerator, I'm going to get a 0, aren't I? If I put a 2 in the denominator, I'm going to get a 0. So the form, this approaches this form, which tells me it's my favorite, least threatening indeterminate form. And because it's a rational function, it absolutely means I can factor and cancel. Okay? So, can you go like this? This is why I'm just lazy. Is that correct? So we have to remind ourselves of some of the rules. Is this a true statement mathematically, what I have right now? And sometimes you go, I don't know. All right, so again, let's get in our Wayback Machine. Let's go back to baby algebra. Baby algebra. Here's the question. The only instruction would be, can you simplify this? Right now, when you're staring at this, we'd say the domain is the real numbers except for, some of you may never have seen that notation. That's the easiest way to say all reals except. The backslash means delete. Some textbooks will actually use a subtraction symbol. I'm saying the set of real numbers with this set removed. That's actually the easiest way to state this, because otherwise you have to use intervals. Do you want to say intervals? Negative infinity to negative 2 union, negative 2 to 2 union, 2 to infinity. That's correct. It's way too busy. Way too much interpretation. In words, wouldn't you all say all real numbers except? Yeah, that's what this says. I prefer this just because it's easier to interpret. The subtraction symbol also works because set subtraction means you're removing things from a set. This is set deletion, set subtraction, no difference. Okay, so I'm doing some algebra, and we all agree that I'm going to get what? X minus 1 over x plus 2. So you're in a baby algebra class and you got this result. There's just one thing I have to consider. You're walking in the room right now and you see this. What do you see when you see this? You say, oh, my domain is all reals except negative 2. There aren't a lot of absolutes in math, but there is one. A domain cannot change, period. There's no exception, but unless it's this case. No, a domain cannot change. If you're differentiating, you're integrating. A domain cannot change. We know when I differentiate, my domain could technically get smaller, because maybe now something went in the denominator, and now I can't use the number. So when you differentiate, you lose endpoints from your domain. And when you integrate, you cannot increase your domain. But I definitely did not increase my domain to now, I can now have all real numbers except negative 2. Didn't we say we couldn't have a 2 either? So I'm talking remedial algebra. This is what you did. This is what, hopefully, every remedial algebra student was shown. I call it the disclaimer. You said, this is equal to this, as long as x is not equal to 2. Does that ring a bell? Hopefully that's exactly what you did, because if you didn't learn that, then you were told a lie. You were told that you could change a domain. In fact, you were told you could increase things and eventually get all real numbers. No, you had to throw in the disclaimer because it would not be a correct answer otherwise. The domain of this and the domain of this have to be exactly the same, but I don't see the 2 because I removed it from the problem. That's why it's called a removable discontinuity. So now go back to here. Can I say that the limit of this is equal to the limit of this without saying anything else? Yes, because a limit does not mean what is happening at the value. It's what's happening as I approach the value. It is true mathematically that this quotient is equal to this quotient for all inputs except 2. But we're not asking what's happening at 2. We're only happening as x approaches 2. Oh, so as x approaches 2, what is this quotient approaching? It's approaching 1/4, so the limit is 1/4, not the functional value. The functional value does not exist. So you're going to explain this. You're the Calc 3 student who understands this inside and out. And you're explaining this to the Calc 1 student. The easiest explanation you can get is the graph of this, which would be something like this. Let's see. I think it would go this way. Let's see. Hold on, which start are we on? No, I think I got it backwards. I think it's going to go something like. It's going to go something like this. You don't have to know that exactly. Okay, something nasty. But there is a point out here, 2, 1/4. there's going to be a vertical asymptote at x equal -2. And the limit as x approaches infinity for this is clearly +1. That's why I'd have a horizontal asymptote 1 unit high. I'd have a vertical asymptote. I said, don't worry about the scale. That's at -2. And I'd have a hole here. This was my removable discontinuity. As x approached 2, y approached 1/4. So in actuality, I'm moving along a curve. As I'm moving along the curve, I don't see the hole. It's 1 point removed. But that's where I would go if I could get there. A limit is, where would you be if you could get there? Can you actually get to 2? No, but if I got right on the edge, I'd be a y value of 1/4. It's been removed from the problem, so graphically speaking, I have something like this. The limit is 1/4. The functional value does not exist. 2 isn't in the domain. It doesn't have to be. Not when I'm taking the limit. So I don't need to put a disclaimer. I have to just remember, oh, the limit of the quantity equals the limit of the quantity means these quantities are equal for all inputs except perhaps that one. That's what it means when you're manipulating a limit. This is what we learned in Calc 1 early on. Now let me show you a different Calc 1, a couple different ones, because we're going to do the Calc 3 limit in a moment, and you're going to see there's some tremendous similarities in the algebra approach. You don't have to relearn how to do limits, in other words. You get to use some of your old notions. So what if we have something like this? I've got the limit as x approaches 4 of the square root of x minus 2 over x minus 4. This is fairly simple. Okay? This is not a rational function, though, because my numerator is not a polynomial. Now, is this still approaching the form 0 over 0?
Yes.
Yes. But it's factor and cancel? I don't really factor the numerator. In fact, I can't really factor the denominator. So we learned an algebraic trick. The problem child in the problem is not the numerator. The problem child is always the denominator. It doesn't matter if the numerator is approaching 0. It matters that the denominator is approaching 0. What if the denominator were not approaching 0? Well, then I could evaluate this. There wouldn't be any calculus involved. So what was one of the algebraic tricks we did with problems like this? You remember? Multiply by what?
Conjugate?
Conjugate of the numerator or denominator?
Denominator?
Not the denominator, because then I'll just cancel them and I'll be back to the start. Try the numerator. And multiply by the conjugate of the numerator. By the way, is that a legal move? Yeah, because that's never 0. Remember, there's only one absolute when you're manipulating. I want to multiply, I want to cancel. You can never multiply or divide by something that can potentially equal 0, because when you do that, you potentially either remove or add to a domain. So you have to be alert. So what did we do in this case? We technically divided numerator and denominator by x minus 2, which means we removed it from the domain. That's why we put the disclaimer. Because I could not have simplified this without canceling it, but I removed it. So I'm multiplying, but this is a strictly positive quantity over strictly positive quantity. That's legal. And what does that give me in the next step then? What does it give me on top? Think of this as a minus b times a plus b. Won't that be a squared minus b squared, which would be x minus 4. That's why we chose that. So should I multiply out the bottom? No. No, don't multiply out the bottom. You'll lose the fact that you're going to have a common factor. Now I think we can cancel. I think that's the way we want to go. What would that leave me with? That will leave me with just this. I like this. Can I evaluate this? It is true that my original quotient is identically equal to this for all real numbers except 4, because I removed it from the problem. But I'm asking as I approach 4, not at 4. In fact, I can't be at 4. I can only approach 4. That's why it's a limit. One of the most common errors that people do in Calc 1, and they do it in Calc 3, is they drop the limit. Now, I'm going to do something absolutely incorrect. This is the worst thing you could ever do. That's a function, agreed? I just said that the limit of this is equal to this function. The only thing worse than this answer, which is 100% incorrect, is to now say, and now I'm going to evaluate the function at a number. There's no function that exists except a constant function. If y equals a constant, then evaluating at every number produces the same constant. A function is never equal to the function evaluated at the number. F of x is not equal to f of c, where c is a constant I evaluated, unless it's a horizontal line. It is never true. Yet we make this kind of mistake all the time. The moment you drop the limit, that is the answer. You've answered the question. If you write it's equal to something else, you now put an equal sign between two quantities mathematically that are not only not equal, can't actually ever be equal. There is no real number that exists that would make this quantity equal to this quantity because 4 is not in the domain in the first place. Therefore, I cannot evaluate this at 4. It's not in the domain. So to write this here is the most absurd error that can be made. I wrote a limit which should have produced a constant equal to a function which is not, and then I wrote a function equal to a constant which could never be equal because I took a number outside of its own domain. So the moral of the story, don't drop the limit until you evaluate it. Because then you're going to have a series of statements that are all not true. But I got the right answer. No, you have equal signs between 3 incredibly different things. You can't say 0 equals 1 equals infinity. Yeah, but infinity was the answer. But you have multiple wrong answers and equal signs between them. So as a calculus student, when I'm ready to evaluate, I evaluate, and that's where I get the number from. But don't ever drop the limit before you've evaluated, because then that has to be the final answer, and the function cannot equal the function evaluated at a number. That'd be like saying I forgot to take a derivative and I wrote the function equals the derivative, or the function equals the antiderivative. It's not true, right? In general, that's not a true statement. So both of these, now, these are both algebraically very simple. But then there are problems that I don't like. So I'm going to do a simple one. Okay. This is called a piecewise function. We don't like these in Calc 1 because they're harder to work with, but they're very easy to illustrate an idea. Of course, I can ask you any real number and it's an easy question, but I'm not going to use any real number. I'm going to use 0, because that's the only number that anything interesting is happening. Do you ever have to draw a picture in order to answer a limit question? Did I have to draw a picture of this to answer the question? No, I just answered the question. But sometimes the picture helps us understand what we just answered. We answered the question here and we got a number, and then I wrote a picture after the fact that said, this is what you actually just said. You had a removal of discontinuity. Oh, okay, that makes more sense to me. The answer is still that, but sometimes the picture helps illustrate. When you suspect that the limit in one direction is not the same as the limit in the other direction, you had to do one-sided limits. We didn't do a one-sided limit on either of these because there was no issues. I didn't suspect it was going to be different from either side. But on here, do you agree that I'm going to have to use one-sided limits? Because my function changes definition at 0. Okay? So this would be the limit as x approaches 0 from the left of which function? The top one, the x squared, because it's only defined for less than 0. This would be the limit as x approaches 0 from the right of the bottom function. And what would this answer be on top? 0. And on bottom it would be 3. So what is the answer to this question? Let's take a chance. Remember, there's only 3 possible answers to any limit question. Finite, infinite,
Does not exist.
does not. Oh, I'm glad you said that. Undefined cannot be the answer to any question unless, and I'm talking in all of the world of math history, I'm asking for the slope of a vertical line. That's the only time the word undefined is ever ever used in math. There is no exception. There's no other use of the word undefined, which means undefined cannot ever be the answer to a limit question. You can't divide by 0. Oh, but what if my tangent's vertical? Then it probably means my limit is either infinite or negative infinity. Undefined cannot be the answer to a limit question ever, because it means you evaluated something at 0 in the denominator. And that's not a limit anymore if I did that. Oh, so if I suspect something's going to be undefined, then the limit's probably infinity or negative infinity if it exists at all. What's the third option? D and E. And that's what this is. When does a limit not exist? The simplest one is when the limit from the left and the limit from the right are not the same. Okay? So it's kind of like saying, you know, I said, remember when we were little kids and we used to play at the railroad tracks and we'd throw rocks at the train? And I'm like, yeah. We ran into each other after many years and we said, let's go meet at the tracks tomorrow. Now, I'm coming from one side of town, you're coming from the other side of town. And unfortunately, overnight, there was a massive, 27.0 earthquake. The rock was involved, saving people, improvement helicopter, the whole 9 yards. So I go to the place where I remember the railroad tracks. Of course, the railroad tracks are split, and you're like 3 miles away at your railroad track. And I'm waiting for you, you didn't show up, you're waiting for me, I didn't show up. Why? Because here's what happened. The limit from the left and the limit from the right were different, therefore the overall limit did not exist. One-sided limits always exist as long as they're within the domain. Both of these one-sided limits did exist. When I say one-sided limits always exist as long as they're in the domain, if I have something like, let's say, the square root function, there's no limit from the left of 0 because that's outside the domain. That's what I mean by it. You can't be outside the domain entirely. But the limit from the right exists. So one-sided limit is generally going to exist unless it's a domain issue where I'm not actually there. So we said this is a D and E because the limit from the left and the limit from the right were not the same. So keep that in mind. Because now we're going to segue to the three-dimensional stuff. And the way we answer the questions is a little bit different, but again, our results are still the same in that I can have finite, infinite, D and E as a possible result. So, I'm going to do fairly simple stuff. Give me a second here. All right. This is a rational function. It just happens to be a function of 2 variables. My domain would be the entire xy plane except where possibly what? The denominator equals 0. Do you suppose there's going to be ordered pairs where the denominator is 0? How about 0, 0? I mean, obviously the denominator is 0 at 0, 0. The denominator's got lots of places that's 0, 0. Or, excuse me, that is 0. So my domain would be the xy plane except where that happens. So let's see if I can just evaluate this. Because if I can evaluate this and I don't get a 0 in the denominator, I'm good to go. So if I put 1, 3 in the numerator, this would be 6 plus 21 minus 27, that's 0. How about the denominator? If my denominator is not 0, then what's the answer to the question? 0, because my numerator is. All right? So 9 minus 18 plus 9. Darn. Now, you're Calc 3 students. Don't ever do that. This just screams bad news. When I have calculus students do this. You do realize, because I used an equal sign, I am now done. There is nothing else I could possibly write. Because I just said the value of this limit equals that quotient. That's not only not a true statement, but that quotient doesn't have a value. It's an indeterminate form. It cannot be the answer to any question that exists because it is not a value. You can't put an equal sign between this and this. Because you're saying the numerical value I get is equal to this, but that's not a numerical value. It's not an answer. You can't use an equal sign. Do calculus students do this? Yeah, all of them do. And they struggle and they can't figure out, I have equal signs between everything. No, don't use equal signs. Now, the other thing that calculus like to do is, and then I'm going to put this, and then I'm going to put this. They love to use an arrow as an equal sign. You realize mathematically, in every conceivable context, in every conceivable math course, arrow does not mean equal in any context, in any math course you've ever taken in any possible way. Now, arrow does have multiple meanings depending on the context of the course. But in none of them does it ever mean equals. And in calculus, arrow only has one meaning. It means approaches, never reaches. And it's only used in a limit. The only time in Calc 1, 2, 3, differential equations, complex analysis, advanced calculus, which is a proof-oriented course you take as a senior math major, arrow always means the same thing. Approaches, never reaches. So here's what calculus do. Even people in this class, I get this. Do you know what that means? 3 plus 4 does not equal 7. This is equivalent to this, absolutely 100% of the time in mathematics. You're saying it approaches 7 but never reaches 7. You realize the absurdity of that statement. Don't use an arrow for an equals ever. Now, having said that, I have students who, every single problem this semester that you've turned in, you've used an arrow for an equals in every single thing you've written. And I'm like, I get tired of correcting it. Arrow doesn't mean equal ever in mathematics. The only other time it means something different is in symbolic logic, in discrete math. Implication symbol means if A then B means A implies B. That's what this symbol means, implies. In symbolic logic, when we're not using words or statements, we say P and Q, we'll use a single arrow to mean this. And I don't like that because in the same course, we'll use this when I say mathematical statement implies mathematical statement, and then I'll do this. For the abstract P implies Q. This doesn't actually represent a specific statement. I don't like that we actually use different symbols to mean the exact same thing. In my entire lifetime in every math course, every course I've ever had, that's the only time that this means something different. It's in a logical connective, it means this in certain contexts. And this doesn't mean equals either. This means statement A implies statement B. So if A is true, then B is true. That's not numerical, right? So, what do? I factor and cancel. Can you factor this? If you could factor quadratics in baby algebra, you could factor this. Do you know why? Each term is second degree, so you already know you can factor it. If all those terms were not second degree, this would actually be a very challenging factorization. Would any of you be able to easily factor a cubic or a fourth degree polynomial easily? No. You might not be able to factor it all, but it definitely wouldn't be easy. But all of you, if it's factorable, you could all factor quadratics rather easily. I don't think I could come up with one that you couldn't answer. So these are technically quadratics. So, I'll help you out. It's that one. Now, here's what you know from the fundamental theorem of algebra. Right? If I evaluate a polynomial at a number and it equals 0, then x minus that number has to be a factor. I evaluated this at 1, 3. So some version of this has to be a factor. I can't get the numerator to be 0 unless 3 times this and 1 times this produced a 0. Does that make sense? Oh, okay, so what's left? 2x plus 3y? You don't have to be that clever to do this. So and then, by the way, I always multiply it back out to double check. So can I now say this? Is this a legal statement? The limit of the first thing is the limit of the second thing. Technically, I factored and canceled, but I didn't factor and cancel a number. What did I factor and cancel this time? This is a little tricky. Remember, our domain is not the number line, our domain is the floor. What did I just factor and cancel? I factored and canceled 3x minus y. Do you agree? But more specifically, I factored in... What did I get rid of? Not just x minus 2, but x minus 2 equals 0. So I got rid of technically x equals 2. So what did I technically get rid of here? So on my floor, y equals 3x would be a line, the slope 3 would go in that direction. It would be a line on the floor. Now, project the line straight up and down. Think of it this way. There's a fissure. There's a fault line. That's probably a better way. A fault line. Y equal 3x is a fault line. None of my answers can be on the fault line. It can be on one side of it or the other. And I asked you something as I'm approaching something on the fault line. So we factored and canceled the fault line. Here we factored and canceled the hole. Because you're removing a point from a number line, now I'm removing a line from the xy plane. You see the analogy? I'm moving more than just a point now. But I can now evaluate this, and what would the answer be? Anybody? If x is 1 and y is 3? Oh. What's my numerator? Maybe I should do this. My numerator's 2 plus 11. What's my denominator? Ooh. Did I completely remove the fault line? I had a fault line squared, didn't I? So what does this mean? This means that from one side I get one thing, from the one side I get another, so this is going to be a DNE. It's going to be a DNE because I'm not going to get a value. Well, won't it just be infinity? No. Depends on which side of 1s and 3s I'm approaching. My numerator is approaching 11 regardless of which side of 1 and 3 I am. Agreed? But depending on if I'm to the right of 1 and to the left of 3, or to the left of 1 and the right of 3, the bottom's approaching 0 positively or negatively, I have two possibilities. Going back to baby algebra, I want to remind you, we've done this problem 1,000 times in baby algebra. We hated it every time we did it. Keep it simple. Remember this one? The limit from the left is negative infinity. The limit from the right of 0 is positive infinity. And this is one of those times where a graph really, really is useful. That's what it looks like. So the limit as I approach 0 from the left, the limit as I approach 0 from the right. Both one-sided limits exist, but the overall limit did not exist because I did not approach from the same direction. Now, throw a caveat at you. What if everything we did in this problem, what if my denominator, instead of squared, what if my denominator were cubed? Then at this point, what would my denominator be? It would be squared, correct? Can I approach 0 from the left? Can the quantity approach 0 from the left anymore since it's being squared? No. My denominator is approaching 0, but only positively. Therefore, what would the answer to this one be? Positive infinity, more specific. Yes. Does everyone understand that? Oh, because my denominator is approaching 0 from the right of 0 regardless, because I'm squaring it. Oh, now, let me go back to this question here. X squared, x squared. What does that do graphically now? It's essentially that. And what is the answer to this question? because I'm approaching infinity from both sides because of the square. Does that ring a bell? Okay. Now, usually, if you can factor and cancel, you're probably getting a happy problem. There is an unhappy problem. Let's look at the unhappy problem. This is the one that gives people the most trouble, the next one I'm going to do. And I don't want you to dwell on this because we're most of the time going to work with things that everything works out nicely. But because we're reviewing limits and we're doing it in 3D, we have to understand the stuff that gave us trouble in Calc 1, how does it translate to 3D? Factor and cancel is still factor and cancel. I still might have to conjugate something in order to manipulate it. The one thing you won't be able to use though, sorry, you'll never be able to use L'Hopital's rule again. I love L'Hopital's rule. Everyone thinks I hate it. But quite frankly, outside of the exponential forms, you never have to use it. And I can guarantee you I can do every limit problem faster without using L'Hopital's rule than I can with. Because the algebraic solutions are usually much easier. Because L'Hopital's rule requires you to take multiple derivatives and then interpret it correctly, and sometimes you have to rewrite it. Algebraic solutions are usually fairly simple, but if you have an exponential form, there's no way around it. I call L'Hopital's rule, I always refer to it as synthetic division. Now, everybody learned long division and synthetic division of polynomials. Long division has no restrictions. Synthetic division has major restrictions. First of all, you can only use one variable. You can't have x and y. Secondly, your denominator has to be linear. Oh, so I can't do it if I have x squared on the bottom. And thirdly, your lead coefficient of your denominator has to be a 1, which is actually an easy fix. Just multiply top and bottom by the reciprocal of the lead coefficient. That's not a thing. But it's the bottom has to be linear. So I can have polynomial divided by x minus 3. That's easy. Polynomial divided by x squared minus 3. No, that's long division. So here's the irony. You get to Calc 1. Everybody in baby algebra loves synthetic. It was so much easier, so much faster, and you never had any issues. In Calc 1, do you know, in a typical Calc 1 class, I'd say less than 10% of the people can do synthetic. But in remedial algebra, that's all you wanted to do. But in calculus, nobody remembers because they all say the same thing. I can always use long division. I can only use synthetic in situations, so I'm not going to bother with synthetic. Yet when synthetic applies, it's always way easier and way faster than long division. But because you can't always use it, people just discount it altogether. Bad idea. So I tell people, no, just know when you can use it, and then when you can use it, because it's such a valuable tool, but it has restrictions. That's what L'Hopital's rule is. You can't use it on all limits. In fact, you can hardly ever use it, but when you can use it, and it makes sense to use, it can be way faster than factor and cancel and all this. As long as you know when you can use it, okay? Problem is, it kind of has a big restriction. It only works with one variable. In other words, you can't use it on any two variable problem. Oh, the ones we just did. You can't use it on anything like that. So how many times will you use L'Hopital's between now and the day you die? Well, unless you're tutoring Calc 2, probably never again. I teach differential equations. Haven't used L'Hopital's rule once, because you don't really do limits in that class. Yeah, L'Hopital's rule was cool and helped us derive formulas, but yeah, you're kind of going to wave at it, as you pass by. Every semester I'll have students say, well, maybe there is a way to use it. Maybe I should try to come up with a way and prove it. I always say, I'm not joking, that's a great idea. You think you got an idea, go, see if you can prove it. Problem is, it's been around for a few hundred years and nobody has proved another version of it. In other words, no one's proved a two-variable version, so I don't know. I'm thinking one doesn't exist because after a few hundred years, and a lot of really smart people have tried it, and no one's come up with an idea with two, it's probably not going to happen. It's a good brain exercise, but I don't think you're going to get anywhere. And if there was a way to use it, with two variables, we'd be using it. Now, this is a very specific evil problem. Oops. Keep it real simple. Clearly, this is going to produce the indeterminate form 0 over 0. Agreed? Problem is, I cannot factor that denominator, so I'm not going to be able to factor anything, am I? Now, this one here, because of your inability to do anything algebraic, you probably are thinking maybe there isn't going to be a limit. If the limit exists, your goal is to find it. If the limit exists, you can't prove it doesn't exist. It exists, you got to find it. If the limit doesn't exist, you don't want to spend all your time trying to find it. It doesn't exist. Show it doesn't exist. You look at this one going, I'm not going to be able to do anything algebraic to factor and cancel, so I'm leaning more towards it doesn't exist. And so go back to the Calc 1 for a moment. When was it a D&E? When I approached the number in question from two directions and I got different limits. Now, I did the one a little while ago, the break. Right? I did the one where I did a piecewise function. That's why you do piecewise functions, because it's really, really easy to illustrate the whole limit concept. The limit from two different directions gave me different values, the limit doesn't exist. Here's the trick. In Calc 1, you're approaching from two directions on a number line. Now, I have a point on the floor. Maybe the point is 4, 7. From how many directions on the floor can I approach that point? Infinitely many directions. See, on a number line, there's only 2. But now you're on a plane. Do you agree there's an infinite number of directions? Oh, I can't do an infinite number of directions. But what I can do is still show, if I came from different directions and got different limits, that would be enough to show the limit does not exist. On the number line, it's easy because you only have left and right. But what if I approached it along one curve and then I approached it along a different curve and I got different limits? That's enough to say two different directions produce two different limits, therefore the limit does not exist. So what we like to do is, there's multiple ways to do this, but probably the easiest way is to say, approach along the line y equals mx. And in this case, all you have to do is m is not 0. Because if m was 0, then you're at 0, 0, and you can't be at 0, 0. Approach it along the line y equals mx. Now, I have a point here. That means I'm approaching the origin. Remember, this is now my point in question. How many lines am I using if y equals mx? Infinitely many, but they're all lines. I could say approach it along the parabola y equals ax squared. I could say approach it along the polynomial y equals x to the nth power for different powers of n. Does that make sense? Oh, and then all I have to do is substitute. So what we're going to do is we're going to approach it along this line. So that means I'm going to rewrite this now like this. X comma mx. I'm approaching it along the line y equals mx, and I'm not giving a specific value for m. I'm saying m could be any real number except 0. Because if m is 0, then I'm already at the origin, and remember, that's the problem, child. I'm approaching the origin, I'm not at the origin. So on top, what would I have? I'd have x squared minus mx squared. And on the bottom, I'd have x squared plus mx squared. Now, oh, sorry, I should be approaching 0, 0. If x and mx are approaching 0, 0, isn't that the same as just saying x is approaching 0? So could I just do that now? Yeah, because now I only have one variable in the problem. So my numerator is x squared minus m squared x squared, and my denominator is x squared plus m squared x squared. Can I factor and cancel all the x squareds? Would that be legal? Yeah, because every term has an x squared in it. And by the way, you notice I'm not saying 0 from the left or from the right. I'm just saying 0, period. Now my numerator would be this, and my denominator would be this. Does that look correct to you? If I cancel all of the x squareds. But if m represents the slope of a line, then m's a constant. What is the limit of a constant? Always the constant. Ooh. Can I do this? Yeah. The limit of a constant is a constant. So we've answered the question, folks. as xy approaches the origin, the limit of this quotient is equal to this along the line y equal mx. So that sure looks like that's my answer. My answer is that constant, except, wait a minute, what does m represent? The slope of a line. How many lines? Every line. So what if I'm approaching on the line y equals x? That means m is 1. And that quotient would be 0. But what if I'm approaching along the line y equal 2x? Then m would be 2 and that quotient would be negative 3/5. That's different. In fact, for every conceivable line you can think of, you'd use a different m. And every time you use a different m, I'm getting a different answer, aren't I? Oh, so that means because different values of m give me different results, all I need is 2 different results, don't I? So we'd say it like this. Different values of m give different results. Therefore, the limit, what? Oops, can't spell. The limit, what? Does not exist. Good. Now be mindful. I just did an entire limit problem and I got something. This quantity is a quantity. This is a value. What I get a lot of students tell me is, the limit is this, and this value does not exist. No, I'm pretty sure this value exists because I just found it. This value does exist. You all okay with that? This value exists. Don't tell me the value. That's like saying the limit is 3 and 3 does not exist. That's not a good answer, by the way. No, I got that value, but different values of m produce different results, so the overall limit doesn't exist. No, that value does exist. What if? I think this limit does not exist. I do this entire problem and I get a specific constant here. I just approached it along infinitely many different lines and I got, the number 3. Does that mean that is the answer? Remember, all paths would have to lead to the answer. But I just tried to prove it didn't exist, went along infinite paths, and I got a specific constant. My small brain would probably say, that's probably the answer. Now, rather than try to show it doesn't exist, maybe I should be trying to show it exists and that's the answer. If you approach along infinite paths and all of them produce the same numerical answer, that doesn't mean that that's the answer because you didn't approach along all paths. So rather than trying, but you're only doing this to prove it doesn't exist, not to prove it does. If I had gotten a specific constant at the end, that would probably have been the answer. But that doesn't, I need to do it the conventional way, probably factor and cancel and do the easy stuff. If the limit exists, you can't prove it doesn't. And if it doesn't exist, you can't prove it does. So in the process of trying to prove it doesn't exist, if you have overwhelming evidence that it probably does, then it probably exists. If I'm doing a limit problem and I'm just not sure what to do, and y'all did this in Calc 1. I don't know what to do, so I just start taking numbers and limit as x approaches 3. You all did. Let me take 3.01 and plug it in. Let me take 2.99 and plug it in. You remember doing stuff like that? There's no validity mathematically in any possible way. But I start messing around and I keep getting the same things. Or I'm taking numbers and I'm getting astronomical results. So every time I put in a number, I get astronomical results. I'm thinking, I don't know, maybe infinity is probably where it's going because I'm getting absurd numbers. Well, that's not the answer, but did that maybe clue you in on maybe that's the direction I should be heading? I mean, that's why that could be useful. So in general, you can't guess at a limit. You can't trial and error a limit. If the limit exists, then it probably should be easy to find. The nature of the problems we're doing. We're not going to be doing complicated things. We're going to be doing simple rational functions and stuff, just to remind you of the process. And for the DNEs, I'm still going to take simple rational functions, but ones that you clearly can't factor and cancel. That's the thing. Okay? So this is not supposed to be a complicated process. So the multiple path rule you can always do. I could have chose, let's say, along any parabola or along any cube. The reason I liked this one was because at the beginning of the problem, all of these had the same degree. Now let me throw a what if at you. Now let's do the multiple path rule to the bitter end, and let's use the same one we just did, okay? Do I get the same result now? What do I get now? As x approaches 0, I get negative m squared over m squared, which is negative 1. Does everyone see you get negative 1? Now, would that make you think maybe negative 1 is the answer? Well, if I'm approaching along lines, negative 1 is the answer. But maybe lines weren't the best approach in this case because of the degree difference. See, the reason you chose lines the first time, I'm telling you, the reason you chose lines is because you had all the same degrees and then all your x's are going to cancel. My x's didn't all cancel. So what might have been a better approach? Now that I saw that reasoning, I'd still like all my x's to cancel. What would be a better approach now? What if I did that instead? Now let's carry that problem all the way through. Do I get the same result I did a moment ago with the lines now? Yes, and that didn't exist because different values of m gave me different results. Oh, so remember what I said a moment ago? When you do everything and you get a specific constant, your brain says, hey, maybe that is the answer. But I still can't factor and cancel. But I really would like to have a situation where my x's can be removed from the problem. And that's why in this problem, this would have been a better choice. And now I got, again, and now clearly different parabolas gave me different limits.
So you just need the one specific case where you can show that the limits aren't the same depending where you approach from, and then you can say it doesn't.
Yeah, this is where it's confusing. There's an infinite number of paths through the origin. I mean, lines, parabolas, it doesn't matter. There's an infinite number of paths through the origin. And there are a great many of those paths that will produce the same answer. But all I need is two paths that produce different answers. That's all I need. That's why there's a little bit of strategy. And I'm showing you two different versions. When I had all the same degrees, lines make the most sense because of the cancellation I'm going to get. Now I chose an example where they're not all the same degree. One more situation. What if these were not the same degree? It's the denominator that I need the x's to cancel mostly, though. So what if my numerator, let's do one more horrible example. What if that was, or actually, let me leave the 4 here. What if, what would be the easiest? No, I'll leave it as a 3. Sorry, I'll leave it as a 3. I would still probably go for whatever the denominator is. That would be more evil and horrific. But I can still do the process because I can't have, I don't want the denominator to be potentially being equal to 0. I want the numerator to be 0, but I don't want the denominator to be 0. There's no absolute, this always works for every problem, but if all your degrees are the same, algebraically use lines through the origin. Now, let me throw one more, let me throw a different nasty at you, okay? This one, this is probably the most hated. Okay. This is hateful. This will be a DNE. The numerator is approaching 2. Your denominator is approaching 0. That's not an indeterminate form. That's an asymptotic form. Indeterminate would be 0 over 0. It's an asymptotic form. So going back to Calc 1, go, oh, My denominator's approaching 0, my numerator's not, which means my quotient is growing without bound. What I don't know is it growing without bound positively or negatively, which means positive infinity or negative infinity are possible right answers. But because I'm not telling you which side I'm approaching, my tendency would be more towards a D and E kind of situation. So of course, let me take this path here. I'm using my left eye so you know something's up, right? Can I do that problem we just did a moment ago by going all lines through the origin? No, because none of them pass through 1, 1. I don't want lines through the origin. I need lines through 1, 1. Oh. In fact, going through the origin would be a terrible idea. I need to go 1, 1. So how would I get lines through 1, 1? There. That's all lines through 1, 1. Point slope formula. Now, algebraically, is this going to be a little messier? Oh, yeah, it's going to be way messy. I got to square something icky. This is all lines through 1, 1. So what I would do is replace y with this, and then I would carry on that problem to the bitter end, and I would show that multiple paths give multiple limits. But that's icky. I don't want you to concentrate on icky, but understand that not everything is going to be a slam dunk and all problems can be done the same way. Things through the origin are the easiest ones, because there's an infinite number of paths that I can easily state through the origin. But if I gave you a specific ordered pair, and I wanted to still do the lines thing, then I'd have to use the point slope formula to create lines through that point. And as long as these exponents are not big, that's not a terrible problem algebraically. It just isn't. Okay? Any questions? So the calculus, quote unquote, we're doing today is really taking a few limits. That should not give you a lot of issues. And I did not ask problems that were overwhelming. But I need to understand the limit concept because next day we're going to derive all the derivative formulas for 3D, and you're going to love it because if you can take a derivative in 2D, you can easily take derivatives in 3D. But there are sort of different rules because of the multiple independent variable thing. And as we go through all the rules, I promise you, by the end of next class, you will have no struggle whatsoever with derivatives. You can differentiate anything that exists. We just have to go through the how and the rules, and every class is the same. By probably halfway through the class, you'll all say, I got this. Oh my gosh, I can do derivatives in 3D or higher dimensions. There are just some rules we have to cover, and it comes back to when I use the definition of the derivative in 3D, it's a little different than it was in 2D, and once we go over the rules and the how-tos, you guys will be able to just nail it, okay? You got to turn this off.